We will now move on to the next contemporary topic, vision language models or VLMs. We are well aware that computer vision has focused on tasks such as object classification, object detection, instance segmentation, semantic segmentation, so on and so forth. However, while these tasks have had significant impact on real-world applications, they output class labels, bounding boxes, masks, images that are generated, so on and so forth. However, they lack one element, which is communicating with humans in an organic and natural way through text. There have been efforts on tying in language into computer vision tasks, even among the topics that we visited in earlier lectures. We saw image captioning, where one takes an image and provides a text caption about the image, or visual question answering, where given an image, there is a question that is asked, such as how many slices of pizza are there in this image, or is this a vegetarian pizza? And the model answers this question about the image. These have been there for a few years now. More recently, there have been more such tasks that have been addressed. An example, text-to-image generation. Thanks to the success of more contemporary generative models, we now have fairly good text-to-image generation, or even text-to-video retrieval that has emerged in the last year or so. Seeing from the other point of view, in terms of natural language processing, the standard tasks that NLP attempts are search engines, spam filtering, machine translation, sentiment analysis, and many more of such tasks. They have an inherent limitation too. While they are pretty good at analyzing and generating text, they cannot process visual cues, obviously, or verify interpretations against real-world visual references, especially when there are linguistic ambiguities. Language models began with the objective to understand and generate text. They have been largely based on the transformer architecture in the last few years, and the attempt here is to learn from raw text. These language models have morphed into large language models in the last few years, or what are called as LLMs, where the key differences are that the LLMs are pre-trained on very large data sets. They typically have a very large number of parameters, of late of the order of billions or hundreds of billions, and the data sets used to train LLMs are web-based text data sets such as Common Crawl, WebText2, Books1, Books2, Wikipedia, and so on, of which Common Crawl is the most common one that's used across different models. The most popular example of LLM is the GPT, or the Generative Pre-trained Transformer, where the input at every step is a sequence of words or a sentence, where the sentence begins with a BOS or a beginning of sentence token, and then you have the sequence of words given as input soon after the token, and you have the target output be the same sentence shifted by one token with an end of sense token at the end. How is GPT trained? One of the key aspects of training such large language models such as GPT is learning via self-supervision. The model learns from raw text and sentences with a target sequence shifted by one token, as we just saw. This enables it to grasp word relationships for accurate output prediction. In the previous slide, for example, when the beginning of sentence token is given, we expect the model to output life, and given the context of the word life, we ask GPT to predict the next word, which is. Given the context of that word is and the previous sequence life is, we expect it to predict a, and so on and so forth. Now, this is also called as an autoregressive model, where words derive context from all preceding words. Each generated token is added to the input sequence, forming the input for the next step. And one key difference of the GPT LLM model from earlier models like BERT is that the GPT model strictly learns context from left to right. BERT was an earlier language model which used a bidirectional approach and used context from left to right as well as right to left. Beyond GPT, there have been many other LLMs that have become popular over the last few years. Let's just look at a few of them before we move forward. Lambda is an LLM developed by Google. It was trained on 1.56 trillion words of public dialogue data. It originally powered the Bard chatbot, and a lightweight version of Lambda led to what we see as the Gemini at this point in time. Similarly, Llama was developed by Meta. This is a relatively smaller model, about 7 billion parameters. Keep in mind that GPT-3 had 175 billion parameters, but is almost as accurate as GPT-3. Bloom is an open source multilingual model that was trained on data from 46 natural languages and 13 programming languages. Galactica, once again developed by Meta, was used to reason about scientific knowledge. Codex is the model that powers GitHub Copilot. It's proficient in more than a dozen programming languages. It can interpret simple commands in natural language and execute them. PalmE was developed by Google more for robotic tasks, and Chinchilla was developed by Google DeepMind to simplify downstream utilization, considering that it required significantly lesser power for inference and fine-tuning. Why are we talking about all of these models? We'll come to that in a moment. The applications that these LLMs have been used for include code generation, content generation, copywriting, conversational tools, educational tools, so on and so forth. But they do have some limitations. They are large, compute intensive to train, can have bias, and one of the most pointed out limitations is that LLMs can sometimes hallucinate and make a user believe that the given output is actually true. Now, let's try to see where we are going by combining vision and language models. Vision systems are fundamental to how we perceive and understand our world as humans. However, these vision models, as we saw before, lack the ability to communicate with humans organically. And how do humans communicate? Most often, the complex relationships between objects and their locations in scenes are described in human language or text. Vision language model attempt to bridge this gap between vision and language by understanding both modalities together, a capability that the human brain is really good at. The output of a VLM can be modified by providing prompts of different kinds. One could provide a bounding box as a prompt and segment an image. We already saw examples of this with grounding dyno and similar models. One can have interactive dialogues by asking questions about an image or a video, or one can even manipulate a robot's behavior through language instructions. Some of the tasks that such vision language models are capable of solving are image retrieval from natural language text, phrase grounding, performing object detection from an input image and natural text. For example, if you want to retrieve a particular image from a cricket match, you can say a young person swings a bat and retrieve an appropriate image from and perform detection on that image to localize the batsman in that scenario. You can do visual question answering, finding answers from an input image and a question in natural language, or generate a caption for a given image. One can also detect hate speech from social media content that could involve a combination of text and images. A question that one could ask at this point is, these are all tasks that we've already seen with other deep learning models. So why do we need to reinvent the wheel and call a new genre of models as vision language models that can perform the same tasks? There is a critical difference, which is that these vision language models that we are going to talk about in the subsequent lectures can do all of this without knowing or having any images about the labels that it's going to interact with the user on. So it can do many of these tasks in a zero-shot manner, which is significantly different from what we have seen from the past. Whatever models we saw in the past, these kinds of tasks required huge amounts of curated, annotated data for supervised learning of the model. Whereas in the vision language models that we are going to see, we are going to notice that these kind of tasks can be done for completely new images, for even text of which we have no images of. What are the topics that we are going to see in this module? In the immediately next lecture, we will see one of the most popular models in the VLM space, which is CLIP. It stands for Contrastive Language Image Pre-training. In a sense, this was the pivoting model that made vision language tasks scalable in a zero-shot way, the way we spoke about just now. This is an image from the CLIP paper, and we'll talk about this in detail in the next lecture. Beyond CLIP, we will also see variants of CLIP, a few of them, including models like BLIP. BLIP stands for Bootstrapping Language Image Pre-training. We will also see what are called multimodal large language models, sometimes also called large multimodal models, MLLMs or LMMs, such as GPT-4, which can also reason between images and text in a cross-modal manner. With that, we'll end this lecture and come back soon to talk about CLIP.